Hello, today we're going to talk about implicit differentiation, specifically with AD or algorithmic differentiation. So in other words, we're going to show how we can compute an adjoint across a solver using AD. And if you didn't watch a previous video on reverse mode AD and showing how we could implement a custom rule in Julia, that would be helpful to watch. But let me just briefly review kind of a key takeaway from last time. We showed that if we had any operation, let's say X comes in, Y comes out, and this is for now just some explicit operation. And upstream of this, there could be many calculations before we get to X, and after Y, there could be many calculations. And eventually at the end, we're going to get to some output. We'll call this F. I think I called it J before, but sometimes confusing with Jacobian. So let's call it F. And in our nomenclature, any variable with a bar, we defined as the derivative of that final output far away, right at the end of the calculation, end of the program or function, with respect to whatever variable is under the bar, right? So that's what X bar is, and Y bar would be defined as df dy, for example. And we saw that, yeah, we compute forward, but in the reverse pass, as we come back, then Y bar is going to be known, right? That's the known input, and we want to compute X bar. Right? And we talked through how we do that with the chain rule last time. So what we want to do today, and we saw, right, that sometimes we could add a custom rule if we knew a more efficient way to differentiate this. So we're going to take advantage of that today. So let's consider the case where we have, a solver here. So let's imagine that I have X coming in still and Y coming out, but it's not an explicit calculation. It's implicit. In other words, I need some sort of solver. We could represent this generically as some residual R. I'm going to say Y first because that's the way I put it in my code. It doesn't really matter. Y comma X, right? So, and generically we could say this is just some residual that we're going to solve to be equal to 0. So in other words, X is the input. And actually, let me write it very explicitly here so you can see. I write like this: R, the function of Y, which depends on X, and X, and that equals 0. So this is just a generic representation of any set of residuals. So again, X comes in, Y is not explicitly calculated, but it's an output after we've completed some sort of solver. So let me just give a simple 1D example. Let's say I have some function that's like this, and X is a vector, Y is a vector. But let's say I just have one Y just to keep this simple. Y plus, let's say, X1 sine of Y times X2 plus 3, or sorry, let's just say equals 3. All right, so this is a function that I could not write explicitly in terms of Y. I cannot write Y equals something, right? Because I just can't solve it explicitly. But if I know X1, and it's a vector, so I've got two components here, right? If I know these numbers, I know what X1 and X2 are, I can solve this for Y, and I could do this with fixed point iteration, a Newton solver. You know, this is 1D, I could use Brent's method. You pick your favorite nonlinear solver or the most appropriate one. We can solve Y, right? So X comes in, Y comes out, but it doesn't come out explicitly. And the way we've written it, we can always write it, we can always move everything to one side, right? So that that same equation, so that equals 0. So that's why we write it that way. It's just generic saying we've moved everything to one side. We call that a residual equation because we want to converge it towards 0. Okay, so that's just, again, we can have vector outputs, but that's just a simple 1D case. All right, so this case is a little more complicated, but not much more. We can now use implicit differentiation. So again, let me write down our function R. It's a function of Y and X, and it equals 0. So let me take the chain rule here. If I take the derivative of R, notice it depends on X, right? That's what comes in. So I want the total derivative of R with respect to X. But it's got these two inputs, so I've got to take partial derivatives. So it's the partial of R with respect to X. Again, what that means is I take the derivative of R with respect to X while Y is held fixed. And then my other partial derivative, partial R, partial Y. And then by the chain rule, right, because Y varies with X, as I change those X values and resolve, I get different y's, right? So then I follow that up with dy dx. And since I know the residual is 0, if I perturb this, I differentiate, so I get to another solution. If I want to stay at a solution, right, the derivative of this right-hand side is also 0, just a constant. So I see now that I could solve for this Jacobian that I'm interested in, because remember before, right, x comes in, y comes out. I want to know this Jacobian dy dx, or as we saw before, I really want to know x bar, but to get that, I need to know this Jacobian. So I need this same Jacobian again. And if I just rearrange this, I can see that dy dx equals minus, let's see, if I multiply by the inverse on the left, dr dy inverse times dr dx, right? Make sure I did that right. Dr dx multiply on the left. Yeah, looks right. Okay, so this is good news. It tells me, one, that my Jacobian here only depends on these partial derivatives, okay? That's great because partial derivatives are way easier to compute than total derivatives. But the other thing it tells me is that, it's maybe not so obvious from how I've written it, but this is evaluated at the solution. So once I've solved this, right? So I solved this, and now I've got, I'll call it y star. I've got the y that actually solves this residual, because I know x, but I don't know the y here, like this output y, I would call this y star. So I evaluate this at y star, okay? And that's great because that means I only need to, I can compute my derivatives after my solver is completed. I don't need to do anything in between. So this should make sense intuitively. If we imagine a solver, so let's just imagine kind of this 2D space here where, say, these are some level sets of contours of some function here. And let's say this is the r equals 0 point here. And let's forget about derivatives for a second, but just imagine solving this. And you can imagine that I could start at different places. So let's say I started here and I'm using some sort of Newton's method, and it's coming around and it gets to the solution. And then I start at a different place and it gets to the solution. And maybe I start over here and it kind of comes around and gets to the solution. So from the solver, we know, I mean, from an efficiency standpoint, certainly it matters where I start, right? Some are going to be better than others, but assuming I can converge and ignoring, you know, the potential for multiple solutions here, a multimodal space, the actual solution doesn't matter upon where I start, right? And so by that same token, we should expect that the derivatives that I compute, they don't actually matter about where I start or the path that I took to get there. In other words, I should have anticipated that I should be able to complete my solver, and once it's done, then I should be able to compute derivatives. So this is implicit differentiation, and this is different than a direct use of AD. So I could have taken this function here, and if I go inside, there's some solver, or let's just imagine a fixed point iteration that's easier to see. Just a for loop. I start with some guess on y, I update it, and I just keep going through this loop. That's just, if I unroll it, it's just an explicit list of calculations. And same if I did Newton's method, right? I just take each step, each iteration, unroll it, just put it in a big list. I could use AD or algorithmic differentiation through all of that, right? Either in forward or reverse mode. I could do that, but it's inefficient, right? Because first of all, we saw we don't need to do that. Like I don't actually care about all these steps that took to get there in terms of my derivative. All I care about is what the actual answer is. And same with getting the derivatives. I only care about evaluating the derivatives when I'm at the end. So it's inefficient. It's also inaccurate usually. So if you imagine that I'm trying to converge, so let's say I did AD through all of these iterations. I have some tolerance, right, to converge the solver, but I'm now trying to converge the solver and the derivative portion as well. And it turns out I usually need a tighter tolerance, or in other words, that the tolerance of the derivative part lags the solution. So if I want some given accuracy for my solver or for my derivatives, it usually has to be, I usually have to set a tighter tolerance than I would for just the solver. So in other words, doing this direct AD or trying to AD through this is inefficient and inaccurate. So fortunately, as we can see in this formula, I can get around it. I don't have to differentiate through that. I don't even need to know what's happening in that solver. In fact, that solver could be in a different language that I can't AD through. I could call, we're going to do a Julia example today, but I could call a Python solver, and that would be totally fine, because all I need to know is what are these partial derivatives after the solver's done at the solution, right? I evaluate this at the solution, and then I can get this total derivative. Okay, so that's great. But again, if you remember from last time, what I want is not actually dy dx. What I actually care about is x bar, right? So y bar comes in. I'm going to need to use that Jacobian dy dx, but I really want x bar. So let's get x bar. So we'll do the same kind of calculation we did last time. I'll write that out. X bar is, by definition, df dx. And so if I follow up from the chain rule, that's df dy times dy dx. And if I'm being careful here with my indices here, let's say, and by the way, we noticed that this is y bar, right? And this is the Jacobian that we just calculated. So we could put that in. And so let's do that. So this is, well, actually, let me be careful first with indices, because I've been a little bit not too careful here. So let's say x bar I, we're going to consider just one output f, because we do this one output at a time. So this is an I, this is I, and then we're going to sum over j. So this is j, this is j. So that's an index notation. So if I was to write this in terms of a matrix notation, if this dy dx is my Jacobian j, and actually, sorry, I'm going to switch the indices just because I think it'll be a little more obvious, because we usually write it the other way, right? I and j. So let me switch my i's and j's, because I want this to be I and this to be j. So this will be j and this will be I. Same thing as I had before. I just switched my i's and j's. So this is, for example, j I j, and this is y bar I. That's equal to x bar I. Or in vector notation, notice that this is multiplying each row, right? So if I was to draw that, this is my j, and my y bar is multiplying across each row here, right? So a fixed column. So this is so we have to ask ourselves, is it multiplication on the right or a multiplication on the left? We can see it's a multiplication on the left. So this is x bar in vector notation, y bar transpose times j. And actually this should be a transpose too, because if we have a row vector times a matrix, I'm going to get a row vector. Okay, so this is update rule. I think we did the same thing last time, but let's now plug in our formula here. J is this dy dx. So let's plug in all of this stuff. So I'm going to get x bar transpose equals y bar transpose times, I got a minus sign, and I've got a minus dr dy inverse, that's a matrix, times dr dx, and this dr dx. dr dx. Okay, so got a formula here for what I actually want, right? I wanted x bar, not y bar. And by the way, in case I forget to say this, I'm doing everything today here in terms of reverse mode, just because that's what we did our previous video on, and sometimes and reverse mode is powerful in many ways. But if you understand the reverse mode, you can do the same derivation in forward mode. It will look a little bit different, but the ideas are the same. It's actually a little bit easier to derive, I think, that way. But so if you understand the reverse mode, then you'll find the forward mode easier. Okay, so I am going to take this chunk here. And let me just double check the way I did it, just so I can be consistent. Yeah, that's what I did. Just trying to remember if I grabbed the negative sign or not. It doesn't matter. Just like, I'm just going to give this a new name just for convenience. I didn't do anything special here. I just said, let's call this grouping of variables here lambda. And actually, I need to call it a lambda transpose, because this is a row vector times a matrix, so I'd get a row vector. So let's call this lambda transpose. So I'm just defining this for convenience. So I'm just saying, by definition, let's call lambda transpose y bar transpose times dr dy inverse. And if I rewrite that, I'm going to multiply by dr dy on the right. That's lambda transpose dr dy equals y bar transpose. And then if I transpose everything, both sides of the equations, I get dr dy transpose times lambda equals y bar. Okay, so this is the first equation. So what does this tell me? This says if I know y bar, which I do, right? Remember, that's what's coming in here. In my reverse pass, I know y bar and I'm trying to compute x bar. So I know y bar, and this matrix I can compute. So this is my the partials of my residual with respect to y. So this is a square matrix. So this is just a linear system of equations, right? Like a matrix, ax equals b. So if I compute this, or I'm given this I already know, I can solve this for lambda. Okay, and before I forget, let me just say, how do I know this matrix? Either I can compute it myself. Anyway, I could use any sort of AD or whatever I want to compute this, or I almost always already have this, because remember what we're doing in the solver is I'm trying to solve this residual for y, right? And so most often we'd use something like Newton's method or some sort of gradient-based method. So in that process, I would have needed to have computed dr dy anyway in the solver. So if I save that at the solution, I don't need it everywhere, but once I solve it at the end, I just need to save that last Jacobian here, or this Jacobian dr dy, and I just pass it in. So I have this, and I can solve for lambda. Okay, so now I have lambda. Let's go back over to this equation. So if I have lambda, this equation says x bar transpose is minus lambda transpose times dr dx. Okay, so this is my second equation. So it says, okay, I know lambda because I just computed that. So I need this guy. I need my partials of r respect to x. If I can get that, I could multiply these and I can get x bar. So here's the really nice thing, though. I don't actually need to compute this, not directly. So I could do that. I could compute this Jacobian any way I wanted, using some sort of AD. And this is not necessarily square anymore, right? Because the size of y and x need not be the same. I compute any way I want, form that matrix, and then take a vector matrix product here. But it turns out I don't need to do that. And this is not always obvious to see, but one way we might see that, let me try to motivate it two different ways here. So let's imagine what I want here is, and I should say this is what we'll see here is called a vector Jacobian product. But so what I have here is I have a sub problem. I'm looking at x coming in, just the partials, right? And r coming out. And there's no y in the equation. So y is a constant. It's the whatever y I solve for, but x is a variable. And I want to know the derivative of r with respect to x. Well, we saw before, if I was to do this with reverse mode AD, right? This is what we just derived generically. If I had an x and a y, if I have x and a y, this is what I get out. And so the same thing will happen here. What I actually get out, if I do reverse mode AD over just this block here with just R, I would get this thing, x bar transpose equals R bar transpose. So instead of Y here, I'm using R because before we're looking at a Y output, but here I'm just looking at just a residual. I'm just looking at that partial. And then this J was dy dx, but in my case, it's dr dx. Dr dx. Okay, so that's what reverse mode AD does, right? Given some R bar in this case, it computes the this product here and gives me out X bar. So in other words, what I could do is if we compare this equation to this equation, if I choose my R bar to equal minus lambda, then I could compute what I want, X bar, in one shot. In other words, one reverse mode AD call instead of, well, so this would be dr dx instead of R calls, right? However big R is, or ny. I could do that in one shot, no matter what the size of R is or what the size of X is. So let me just try to explain that a different way. Two other ways. Okay, so let's get rid of this so I can stay close to this thing here. What I'm actually trying to do here, remember dr dx is this Jacobian. And let's just say it's got 3 entries here, and it's got, a bunch of things here. Let's say 10. So what does this look like? When I multiply this row vector, it gets multiplied across each column here. So what I'm doing, right, because I took lambda and I'm multiplying it across. So what I'm actually doing is I'm taking lambda 1 times this first row plus lambda 2 times this next row plus lambda 3 times this next row. So this equation here is a weighted sum of the rows, and it's weighted by negative lambda. And again, that's exactly what reverse mode AD does. If you remember from last time, we talked about kind of the seed vector that we said, well, if I go all the way back, remember in this chain here, and I said, I know Y bar. Well, how did I know that? Well, because we started with F bar. And how do we know F bar? Well, by definition, it was DFDF, so it was just one. Or in the regular case where F has many outputs, it would be 0, 0, 1 for the one I wanted, and then the rest zeros. Well, this is the same case here, right? So if I choose, so let's say I've got 3 outputs. If I choose R bar to be 1, 0, 0, so I choose that as my seed, and I pass it back through this block, right? R bar comes in, X bar comes out. Then what do I get? Well, I get this first row. And then if I choose R bar to be 0, 1, 0, then I get the second row, right? So I could do that. I could do it 3 times or ny times in general. But if I choose R bar here to be minus lambda, so I say it's minus lambda 1, minus lambda 2, minus lambda 3, then that gives me precisely this weighted sum that I'm after. So in one pass, one calculation, one reverse mode AD call, I get this what's called a vector Jacobian product. So that's a powerful idea, and in forward mode, it works similarly, except for it's a Jacobian vector product, so we've got the vector being multiplied on the right. And so you can do it in one forward pass, regardless of the size. So in other words, I can calculate this very efficiently. It's one reverse mode AD call. Here's a third way to see it, and this is the way we're actually going to implement it today. Just I think this is a simple way to see it. Imagine I define a new function, g, which is going to be minus lambda times r. Okay, and r is a function of x and y, but y is fixed, so this way it's y star comma x. So g now is, and maybe I shouldn't call it g because it's a gradient. Let's call it h. H is a function of just x, and in fact, it's a scalar function. Oops. It's a scalar function because I've got a vector, lambda is a vector, and r is a vector, so I'm just taking a dot product. So this just gives me a scalar. So I have a x vector coming in. When I compute this, I get a scalar. And so look what happens if I compute dh dx, that's the derivative of scalar with respect to a vector, so this is a gradient. It's minus lambda transpose, because lambda is a constant here, that's just given. And then I get the partial of r with respect to x. And that's exactly what I wanted, right? That's this thing here. So in other words, if I had defined this function here, which gives me a scalar, and I know from reverse mode AD, if I've got a scalar output, that's just one reverse mode AD call. So I just have to call this reverse mode AD once, one call, and I get my desired derivatives. So 3 different ways to look at it, all the same thing in the end, which is that I do not need to, this would be inefficient. I could do a vector, I could form this Jacobian. I could take derivatives in reverse mode, for each row, one at a time, fill that thing out, and then do this vector matrix multiplication. Or I could do this in forward mode, one column at a time, and then do the multiplication. But I don't need to do that. And we see we don't ever even need to form this matrix at all. We don't ever get the Jacobian, but we get the product of the vector times its Jacobian in one shot using a reverse mode AD properly formulated here. Okay, so this is what we want. So that's the rule we got to provide. So once we can provide X bar, then we have now a custom rule for any generic solver, and it's going to compute this adjoint for us. All right, so let's go to the code here. Let's see, make sure I do this right. I got to share a different screen now. Okay, so I'm sharing my screen here. And what I've done here is I've just copied over those two key equations that we derived that I put in boxes. So let me just make sure I did it as I said I did. Yeah, that's exactly what we just derived. Okay, so we're going to need those because we're going to implement this. What I've got here is an example. Let's just go to the example first. So this is, let's just step this one at a time. So here, let's say I've got this residual function, r. It's a function of y and x. Remember, x is what comes in, and y is what I want to compute. But I don't know y yet, so I'm taking a guess, and the residual just says, well, what's r if I if I give you some y and x, and this is the thing I'm trying to drive towards 0. And so we did a simple 1D example before, so now we're going to do a 2D example, and I'm doing everything out of place just for convenience here. Okay, and then I have a solve function. So remember, x should come in and y should come out, and that's what's happening. I'm calling NL solve, which is in the capital N, capital L solve package. And this is, if you don't know the syntax here, this is just to create an inline function. So I could have written this like, just call this some wrapper function. Y tilde is residual of y tx. So I could have replaced this whole thing here, defined the function beforehand and then passed in the name of the function. I just need all I'm trying to do is I have to wrap this because, or create some inline function because I need a function that just takes in one input, y, because that's the thing I'm trying to solve for. And I want the constant x to just be in there. So I'm just done this little closure here. So I've got a function y and I need to give it a starting point. So I've just put in some starting point and it's going to compute derivatives because it's going to use, I think the default is trust region method, but it's, let's say you could think of it like Newton's method or however you want, but it's got to take derivatives. So it's going to use a forward mode AD. And then it returns the result, which is my y. Okay, and so let's ignore this guy for a second. So this is a very simple program, but let's say, imagine I've got some x that comes in and I do some explicit calculations, right? Here's another explicit calculation. I get to the solve, that's implicit, and then I do some other explicit calculations, or there could be more, there could be other implicit stuff, it doesn't matter. Okay, so this is the program I want to compute. So we want to right away so we can automate this solver so that we can get derivatives around it. If I called AD on this right now, it's going to go into the internals of this solve. And so it's going to try to go into NL solve here and into its internal iterations and propagate derivatives through those. And we're saying we don't want to do that. We're going to try to avoid that because it's going to be more efficient and more accurate. So that's our goal here. So let's do that. So here's our, I put in this comment here, I'm just reminding us of our convention here. We're going to say, given some residual function that takes in y and x and spits out r, right? Where y is a vector, x is a vector, r is a vector. And I need to implement these equations that we just did here. So first, let's do dr dy. That's, let's just compute this term dr dy. And again, as I said, we would normally already have that and we'd want to pass it in because here in this step, when we did the nonlinear solve, we're trying to converge this residual r to 0 by changing y with the starting point y. So this is already computing dr dy. We'd want to save that, but I'm just trying to keep it simple here. So we won't do that. We're just going to compute it. So we're going to do it simply, and it's square because same number of equations is unknown. So we'll just do a forward diff. I'm going to compute a Jacobian. And I'm passing in the function and my y and my x. And in this case, x is a constant. So I just need to compute this as a function of y. So we'll say this is this. I'm going to create again another inline function here of my residual evaluated at x. And I want to evaluate that at my point y. Hopefully I did that right. So again, here's some function that takes in y tilde. And it evaluates my residual, and I want to differentiate this function at the point y. So that will give me dr dy. Okay, so that's, again, normally we could just pass that in, not have to, this would be a little inefficient, but that's okay, just illustrating the idea. Okay, second, we're going to compute this vector Jacobian product. And again, remember we said, we're not going to form this matrix here. We're going to compute the vector Jacobian product. So it's one pass in reverse mode AD. So let's call reverse diff, and let's do, it's a gradient this time, right? Because it's just one pass. And the function I want to compute is, notice what I'm passing in here, same things, but also lambda. Lambda is going to come in. So I've got my lambda, lambda transpose times my residual function. And my residual function takes in y and x, but I only want the derivative with respect to x. So I'm going to have this x tilde here. So y is fixed, it's a constant. X is the thing I'm differentiating with respect to, and I want to evaluate it at x. Okay, so again, residual returns a vector. I take a dot product that gives me a scalar. So this function here is just a scalar. X comes in, a scalar comes out. And so I can take the gradient of that evaluated at x. So that gives me this product here, this vector Jacobian product. Okay, great. So I've got a vector Jacobian product. I've got this dr dy. I've got the building blocks that I want. So we're going to define a new function that we're going to call implicit. And we're going to pass in all the information we had before. Our goal here is to replace this line here that has a solve. So I obviously need solve, and I need x still. And the only new piece of information we need is we need that residual function, because we need it for partial derivatives and the vector Jacobian product. So we're going to pass that function in. And so we're going to overload this function. And the first case is if there's no AD, if you just call this function normally, it's just going to call the solve function. So if you're not doing AD at all, just return solve. And now we're going to create a custom rule. So now if you called the implicit function, but you called it with reverse diff or any reverse mode AD package that uses chain rules, this is what we did before. If you watch the other video, we're going to create a rule for the implicit function. So this is saying anytime some reverse mode package gets to a call to implicit, it says we're going to call this instead, and we're going to find our own rule. So we have to give it the other arguments that are already there, solve, residual, and x. This first part here, this outer part, is just the forward pass. So remember, x comes in, y comes out, and that's just a solve. This inner part is called the pullback, or that's going the other way. Y bar comes in, right? And x bar comes out. So y bar is coming in and x bar is coming out. And the format here is that I've got to return an output, a derivative of every input. And all of these other things, I'm not differentiating respect to them. It doesn't make sense to, right? I don't differentiate with respect to the name of this function or these functions. So these are just all no tangent. I'm providing the derivative of x bar. So again, outer side, x comes in, y comes out. The pullback or the reverse mode, y bar comes in, x bar comes out. And so I need to fill this out using these steps. So let's do that. Y bar comes in. Let's do this first thing here. So dr dy we computed before. So let's call this, I don't know, we'll call it j y, I guess. And that'll be dr dy. We have the residual function, y and x. So I'm just calling this function here. And it's going to give me dr dy. And now I need to solve for lambda. So that's a linear solve. And that's the main cost of this, right? And this is going to scale with I have to do this linear solve once for every y bar that I have. So in other words, once for every output that I have at the very end. So lambda, this is ax equals b, right? So lambda is equal to jy transpose backslash y bar. Yeah, so I'm just solving this linear equation here for lambda. And now that I have lambda, I can plug it into my vector Jacobian product. So I'm just going to copy that function here. Lambda goes in. I already know y, because again, this using the y after I've solved it, right? That's all I need to know is after the solution is over, x, I get my vjp, and that gives me my x bar. And that's it. So I return that, and then out of this chain rules rule here, I return my output and I return the function that does the pullback. So I'm going to call this pullback once for every output I have at the very end. And this little bit here we saw before, this is just because reverse diff doesn't actually accept chain rules by default. So this is a macro that allows it to use chain rules functions. Okay, so with all of that, what we can do now is we can modify our program. We could take the same program, everything's exactly the same, but I'm going to replace this line solve with this implicit call. So notice this makes this really simple because I'm now doing an adjoint, but all I have to do is pass the things that I already have. I already have a solve. I already have a residual. So I can take any generic solver, this code that I would already write, and all I have to do is replace this one line of code, and I can get an adjoint. So let's test this. We'll give it some evaluation point, and we're going to call our original program with forward mode. It actually doesn't work with reverse mode. It will actually with a little more effort. NLSolve doesn't actually support reverse mode very well out of the box. With a little modification, it's not too hard, you could do it, but we're just going to call it forward mode. And then our modified program, we're going to call this in reverse diff. We could do forward too, but remember, we only just derived the reverse one here. So we've only overloaded for reverse mode. We can easily overload for forward as well, but we're just going to call it reverse. And we're going to compare these two. Let's print out the absolute value of the difference between these. Print that out, see what that looks like. Let's run this. And give it a sec to compile here this first time. Oh yeah, I know this is not going to quite work. So it's giving me an error that I'm trying to place some duals in a float. The issue here is in NLSolve, I need this, my starting point, to be the same type as X. So if X is a dual number, I can't give it in floats, or else the solver is going to initiate with floats, but I'm going to be passing in duals and it's going to have a hard time. So I'm just going to convert that, the starting point, to be the same type as X. And that should hopefully work then. Okay, there we go. It's a little bit hard to see. And actually, these Jacobians are so small that let's actually just print them both. Okay, that's not much better either. How about I print, well, that's okay. I'll just do the first one. It was fine how it was, I guess. We'll just print the difference. And yeah, notice it's very small, right? We're near machine precision. There's a little bit of error because, again, remember, doing differentiation through the solver is a little bit inaccurate, but these are, very, very close. Biggest one is here, 1 to the minus 13. So yeah, I think that's it. Oh yeah, I should also say we do have a package that already does all this for you, and there are other packages too. In fact, this is not hard for you to add to your own AD things, or in other languages too if you want. But we have a package called implicit AD here on the BYU Flow Lab that does this and some more things. But I did this kind of simple version. It has a little more options, a little more robust, and does forward mode. It has some other options. We do some things for ODEs to do unsteady adjoints efficiently, and overloads for linear systems and eigenvalue problems. But